So we're going to discuss 7.1 roots and radical functions. So that's things like the square root, cube root, fourth root, or nth root. So you can say fifth root, sixth root, seventh root, eighth root, but we do have special words when it's a square root, and implied 2 right here as the index is what that part's called. And we have a special word for cube roots when there is a 3 as the index. So some vocabulary that's important is the index is a little number inside the symbol, and then the radicand is the part underneath, and then the symbol itself is called the radical symbol. So square roots are probably the most familiar to us. It's what times itself is that number. So for example, number 1, the square root of 36 is 6 because 6 times 6 is 36. We can also write that as 6 squared, and then the square root and a square cancel. Or you could say the square root of 6 squared like that would also cancel, but this is the meaning here is the 36 is underneath, so you'd have the 6 being squared as 36. And then the square root and the square cancel. The the negative in front means the opposite of, so it's the opposite of. It's, in other words, -1 times this. So -1 times the square root of 49. So we're going to have to figure out what this quantity is. It's like following order of operations. We need to do the parentheses first. This quantity is 7. So it's -1 times 7. So we get -7. The next one, what times itself would get you -100? Well, if we try 10 times 10 is 100, but not -100. And if we try -10 times -10, we won't get -100 either, because a negative times a negative would be a positive. So there's no way that we can have the same number multiplied by itself give us a negative in the real number system. And so we say no real value. There is a way to represent that using the imaginary number system. It would be 10i, and we'll talk about that at the end of chapter 7. The next one, number 4, similarly, we cannot take a square root of a negative in the real number system. But if we go into the imaginaries, this actually would be the opposite of this. So this would be negative and then 5 from 25, and the I comes from the square root of a negative. So the I is just the square root of a -1. Cube roots are then what times itself 3 times gives you that value. And you can have a positive or a negative, because when you go an odd number of times, you can get a negative. If it's a negative times a negative times a negative, you'll get a negative. Or it can be positive, because a positive times a positive times a positive, an odd number of times is a positive. So here we're trying to figure out what times itself 3 times would be -8. So since it's negative, we know that it's going to be a negative value. And then what times itself is 8. Turns out 2 times 2 times 2 is 8. You can also sometimes determine these values with your calculator if they are going in exactly and there's no decimal. So I have some directions actually up here, the different kinds of calculators that are pretty typical. I'll show you how to use that on a couple of those problems. So here is a standard scientific. There are different versions, but what you're looking for is the square root button, which for this calculator is right above the x squared button. So you're going to use the blue to get to that blue. So shift, oops, I have something there, second, and hit the x squared button to get the square root. And then you type in your number, so 36. You can end the parentheses if you want, but it is implied at the end for scientific, so enter and you'll get 6. If you want to do something like anything other than a square root, like a cube root, what you're going to have to do is say what your index is first. So like cube root would be 3 as the index, hit second, and the caret, you're undoing the power. So you're, by taking a nth root, you're undoing an nth power, and this is the power button when it's not just square, when it's cubed, or third, fourth, fifth, sixth, etc. power. So we undo it with the xth root. So we click that. And so what this is saying is the x is actually 3. It doesn't mean 3 times. If I wanted to do 3 times a root, I'd have to use the multiplication button over here. So if I want the cube root of -8, I'd go down to my negative down here, and then 8. And it gives me -2, which is what we just mentioned. So if I want fifth root, for example, I'd hit 5, second the caret symbol to get the fifth root, and let's go ahead and do 125. So the fifth root of 125 is not a perfect, it's not a perfect fifth root. It has a decimal. And so we generally don't write this down because that would be an approximation, and we simplify it another way, which we'll find out later in this chapter. All right, brief instructions on a TI-84. So the TI-84 has the square root by the square button, just like the scientific would. You'd hit second and the square button to get the square root, and then you type in your number. For a cube root, or fourth root, or fifth root, or any other root, it's in the math option, so you hit math, and you can see that there is one specific to a cube root here, and there's one for any other root. So let me click that one, so it's more generic. It says answer, so what it would do is take that 6. I don't want it to be 6. Let's say I want it to be the cube root. I could just put a 3 there, and I use my arrows to move around. Or if I wanted it to be the fourth root, I put a 4 there. You can also have typed it in first. So for example, you could have said 4 math down to the x root, and it would put the 4 in there. But if you forget, at first you can use your arrows to get back there. So let's say we're doing the fourth root of 64. Again, not a perfect fourth power, so it gives us a decimal. If I did the fourth root, oops, let's see, if I do the fourth root of 81, that is a perfect fourth power, because 3 times perfect fourth root, 3 times 3 times 3 times 3 gives us 81. So that's the 84, and 83 is like that as well. And then the 89, there is a shortcut button where you hit the diamond, the green diamond, and then you hit 9, and it'll say root. So if I wanted the cube root of 125, like I did right up here earlier, you do 125, comma 3. So that would mean you want the radicand to be 125, and you want the index to be 3, and you can double check that you put it in the right direction when you hit enter, and it tells you the answer. So again, you do need a comma in between, which is here by the 9. There's the comma, and you also need to end your parentheses on the 89. And if you ever need a negative, just like on the scientific, it's down here. So let's continue on. You can use your calculator to get these. This is a perfect square, it's 5. Or you could say what times itself 3 times is 5. Here's opposite of, and what times itself 5 times is 32. So with a calculator, you can determine that would be 2, and a negative because it's the opposite of 2. If you took 32 and you made a factor tree, so I know 2 and 16, I know it's 2 and 8, but maybe I decided to do 4 and 4. Or if I did 2 and 8, it would be fine as well, because at the ends, it's when you have your prime numbers, and that, when you multiply all that together, has to equal 32. And so you have 1, 2, 3, 4, 5 of them, no leftovers, so it's exactly 2. Or 5 factors of 2. So in other words, it's a negative 5th root of 2 to the 5th, and the 5th root and the 5th power cancel, so you have the opposite of 2. So this next one is a negative in here, which is okay with an odd index, because again, a negative times a negative times a negative times a negative times a negative would be negative. It actually can happen. So you can have a negative when it's an odd index. You cannot have a negative in here when it's an even index. So this ends up being 243. Again, if we want to try this out, 5th root of negative 243. It says negative 3, but I had this negative out front, so it's negative, and then this is negative 3. So you end up with positive 3 as a final answer. If you had typed into your calculator the negative out in front, insert, oops, not inserting, negative 5, oops, negative, yeah, negative, and then you have to do 5th root of negative 243. Notice I put it outside just to be clear on order of operations and for the fact that we're multiplying and have that 5 there. It might be a little bit of an issue. Otherwise, there's the 3. Next, you have this plus minus symbol. So we're going to have plus or minus, and then you evaluate this. Square root of 16 is 4. And then here it's a decimal, but if we think about what that means, it's tenths, hundredths, thousandths. So this is 64 thousandths. And so we can take the cube root of 64. Notice I'm putting in the index so that it remains an equivalent expression. And then I can do the numerator and denominator. So 4 and then 10, and I can reduce that. If you did it in your calculator, you'd end up with 0.4, which is 4/10 or 2/5. And it wouldn't be rounding because that terminated. The next one is just kind of what I mentioned earlier, that a square root and a square cancel, a cube root and a cube cancel, a square root and a square cancel. This one had the whole thing was squared, so you were left with that quantity when you canceled the square root with a square. And even though you'd think, oh, I'll cancel the square root and the square here, this is an imaginary number. It's not a real number because it's square root of a negative. This is not real. And so then squaring something that's not real is still not going to be real. And then again, this is not real either, because you can't take a square root of a negative. Nothing times itself will give you -9. So a couple important things for this lesson is whether you can have a negative or a positive underneath the radicand with different indexes, and how that works. So if you have a positive, you can either take an even index or an odd. No matter what, you'll get a positive value out. You can see here that's odd and you got a positive value out. That's an even index and you got a positive value out. When your radicand is negative, if it's an even index, like the square root of a negative, that's when it was not a real number. Not real. And then when you took an odd index of a negative, that's when you ended up with a negative. So for example, let's see, where is that example? It's embedded in this problem right here. We had the opposite, but then this was -3. Or here, -8, and it's odd, so we got a negative. So that's pretty important in terms of when is it positive, when is it negative, when is it not real. Kind of summarize the next chunk down here. When you have an nth root and you have something to the nth power, either like that or like this, it'll equal x if the n is odd. So if your index is odd, because then we don't have to worry about whether it was a non-real value, or if it's even and you've got a positive for your index. You just can't take the even index, like a square root or fourth root or sixth root, of a negative. You can take it of a positive. So that this is just a fancy way of saying a positive. All right. Let's do some with variables now. And I'll show the factor tree a bit more as well. So we're going to be able to break this up essentially into its factors. So square root of 49, square root of a to the 4th, square root of b to the 10th. You can literally do that, or you can just kind of do it in your head and say square root of 49, square root of a to the 4th, square root of b to the 10th, and just find the values of each of those. So square root of 49 is 7. A to the 4th, imagine you have 4 a's. So this is like a squared, and when you take the square root, you get a out of it. And then here's another a squared, so when you take the square root of that, you get an a. So you end up with a times a, or a squared. In other words, it's a squared squared, and we're taking the square root. So square root and this square cancel, but you're still left with a squared there. You could draw out 10 b's, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would give you a b when you take the square root, another, and another. So you'd end up with 5. So b to the 5th. Alternatively, you can think of it as the square root of b to the 5th squared. So what was squared to make it 10? 5, the square root and the square cancel. So we wanted the 2 here to cancel out with this square root. So what was needed here in order to make it equivalent to the 10? So 5. And so there's your answer. Some people want to say plus or minus because there is a situation where when you're dealing with square roots, you do put a plus or minus, but that's when you're taking, like you're saying, what has a square root? So like x, let me start over, like if I said x squared equals 49, well then 7 squared gives you 49 and negative 7 squared gives you 49. That's a different scenario. That's when you're solving and there are 2 things that give you this. There's only one thing where when you take the square root, it's called the principal square root. There's a plus right there. Or if you wanted the minus, you'd write it like that. Or if you wanted both, you'd put the plus minus symbol. And that's what you'll see when we do quadratic formula. So that's just a little aside. So now for question 17 here, we have the cube root of 27. So we have to break up 27 into its factors. Factor tree can be helpful. And we're looking for groups of 3 because we're trying to find something that's cubed. So this times this times this, that's saying 3 cubed. So we do have a group of 3 here. So we'll pull out a 3. If you took your calculator and did cube root of 27, you would get 3. And then here it's, imagine 6 y's, 3, 4, 5, 6. We're doing groups of 3 this time. So we have 1, 2 groups. And so it'll be y squared. Okay, we'll have 12, and we're grouping them in groups of 3, so we'd have 4 groups. And then 15, grouping it in 3, we would have 5. So another way you can do these is by taking the exponent and dividing by the index. So for the ones with exponents. So 6 divided by 3 is 2, 12 divided by 3 is 4, 15 divided by 3 is 5. Had this been a negative there, then we would have a negative. I don't like this one. This one has a negative. We'll do the shortcut. So you have to find the cube root of 125. We discussed that was 5 earlier. 5 times 5 times 5 is 125. Negative 5 times negative 5 times negative 5 is negative 125. It's okay to have a negative when it's an odd index. So we can take W. We'll have one group of 3. Y, we'll have 3 groups of 3. And for the X, we'll have 6 groups of 3. So just again, dividing the exponent by the index. So here is a little note. If you have a power with a root, we can just take the exponent and divide it by the index. So that actually is a rule we're going to use later in chapter 7, where we can convert between a radical and a rational exponent, meaning a fraction as an exponent. And you can go either direction. For the graph of these, just project this thing here. You can always do a t-table when you're graphing something that's unfamiliar. If you put a negative in, it's always good to go from like -2 to 2 when you're not sure, and then adjust accordingly. And be strategic if you know anything about the function, like if you happen to know that the square root of 4 is 2 or 9 is 3, be strategic. If I try to put in something like 2 or 3, I'm going to get the decimal. That's fine. You could sketch that. But the best one is to be able to plot actual integers, because then it's more accurate. So we can't plot anything below a negative for x, because again, it would be not real. Even index with a negative, not real. So that's why my starting point is here, and I don't have anything graphed where the x's are negative. So I start at 0, 0, and I plotted these other points, but the pattern really is that when you take the square root of 1, you get 1. When you take the square root of 4, you get 2. When you take the square root of 9, you get 3. So square roots always have this shape. The only way to change that shape really is to change the coefficient, which we don't do in this course. You might see that more in a pre-calc course. So you're going to pretty much see the standard parent function, meaning it starts at 0, 0, 1, 1, 4, 2, 9, 3, because you're taking the square root of these values. If you want to translate it, move it right or left or up or down, then that is what happens when you start adding and subtracting either inside of the root or outside. And we'll be talking more about that in just a moment. But this is the parent, and to bring back the idea of domain and range, since it's been a little while since we talked about it, domain is your smallest x that your graph occupies. So this graph doesn't go anywhere below 0, but it does include an x of 0. That worked. And so I put a bracket to include it, and it keeps going. I could take the square root of 100 or 1,000 or a million, or 532 billion. So I can keep going. So I use infinity, and infinities always have parentheses because, again, it's a concept. It's not a number. You can never actually reach it. You can never include it. The range is your y. So the lowest your curve goes on the y-axis is right here. And so 0, and again, it includes it because it's a closed dot right here. That was an actual point. And then it keeps going up. So when I'm looking at these curves for domain and range, if there is an arrow, then think about the components of the arrow. This is going to the right and upward. For cube roots, you can take a cube root of a negative, and I was a bit more strategic here. I knew that you know, -1 times -1 times -1 was -1, and -2 times -2 times -2 is -8. So that's why I picked those. I could use larger numbers. We talked about 125 being 5 cubed, but it wouldn't fit very well on a graph. So here is the ones that fit nicely on here, and makes this kind of S shape. And this time, the domain, because it keeps going left, I can keep putting smaller x's, as small as I can possibly think of. And I can keep going to the right. I can keep putting in bigger x's into my function. I can go all the way to infinity there. And because I can keep going smaller for the x, and my y will then always go smaller, and similarly bigger and bigger, I can say it's from -infinity to infinity for both domain and range. So you can translate these, move them right, left, up, or down, whether it's square root or cube root. Here is the general notation for it. It has to do with h and k, h being the horizontal shift that goes in the x direction. It always has a minus, and then how much you're moving in the right, left direction. And then the k is the vertical change, the up, down. And so the key point, whether it's where you're starting to make this curve from, or this key point in the center here, that's the h and k. I wouldn't memorize these. I would just look at the function I have and determine the domain and range from that. So I've graphed one here where, because of this negative, this would have been minus a -3. So really it's -3 for the h, and then it says plus k, so it's plus -2. So it's -2 for the k. And so that key point for my square root function, the one that kind of looks like the shape of a square root, sort of, you know, sort of, that key point is at -3, 2. So I went to -3, -2, plotted my key point, and from there, as I move 1 over, I take the square root of 1 is 1, 2, 4 over would be 2, 9 over would be 3 up. And it's always from this key point. And if you did a t-table, you'd see that that matches up with the arithmetic that goes on there. So, oops. So there we go. The domain is your, again, smallest x to largest x, so -3, close dots, so bracket, to infinity. And then your range, your smallest y, is down here at -2. So it goes from -2, and then it keeps going up, so -2 to infinity. So I hope that helps with the basics of roots and some of the graphing.